All right, this infinite series has alternating signs. You can tell because this term is always positive no matter what n we put in. And this term is going to cause the signs to alternate. It's positive for even ends and negative for odd ends. So we have alternating signs, and the terms are decreasing towards 0. So converges by the alternating signs test, alternating series test. Okay, so I have to check the absolute value. So we're going to check absolute convergence using the limit comparison test again. And this time I'm going to compare to the sum of 1 over n. All right, so coming up with the sum to compare to, you just look at the leading term. So I would just look at 1 on the top, look at this 1, and then in the denominator, look at the leading term, the square root of n squared is n. So I'm comparing to 1 over n. And I did the same thing in the previous one. I didn't say it out loud, though. I looked at the 3n over the n cubed. The leading, any coefficients don't even matter. So I just looked at 3n over n cubed, and so I decided to compare that to when you reduce, you get 3 over n squared, and so I used 1 over n squared. Coefficients don't matter. Okay, so I'm going to use the limit comparison test again. So I take the limit as n goes to infinity of a generic term from my sequence. So this is 1 over the square root of n squared plus 19n, and compare it to a generic term from my comparison sequence, 1 over n. So this is the limit as n goes to infinity of 1 over the square root of n squared plus 19n times n over 1. Okay, so the degree in the denominator is really a 1 because the square root of n squared is n. So this is like n over n. So the limit is 1, which is a finite and non-zero, which means that my series has the same behavior as my comparison series. My 1 over n, the harmonic series, we know diverges, which means that my series also diverges. Right, the absolute value diverges. So the original series converged, the absolute value diverges, which means we have conditional convergence.